Hi class, in this recording we are going to talk about how gases in our bloodstream influence the rate that we breathe in and out, our respiratory rhythm. Now, the blood that we care the most about is our arterial blood, because this is the blood that is delivering nutrients to the tissues of our bodies. So let's talk about our homeostatic set points. Our blood pH needs to fluctuate between 7.35 and 7.45. Too high, we have alkalosis. Too low, we have acidosis. Our blood carbon dioxide partial pressures need to be approximately 40 millimeters of mercury, and our blood oxygen partial pressures need to be approximately 95 millimeters of mercury. So these are our predefined set points. To monitor these blood chemistry factors, pH, carbon dioxide, and oxygen, we have chemoreceptors within our bodies. We have chemoreceptors both within the peripheral nervous system and the central nervous system. They're going to monitor the chemistry of both the blood and the cerebral spinal fluid. And of all these three things, pH, CO2, and oxygen, the most potent stimulus to influence breathing is blood pH. Because as we have a change in hydrogen ions in our bloodstream, we're going to have a change in the shape of the proteins of our blood. So more than anything else, blood pH is going to dictate our respiratory rhythm. Because blood pH is going to be determined in large part by carbon dioxide levels, blood carbon dioxide is the second most important variable, and the least significant variable is blood oxygen levels. So as we look at our rate of breathing in and breathing out, pulmonary ventilation, we adjust it to maintain blood pH or homeostasis and pH homeostasis of the brain. So within our brain, we have central chemoreceptors. Those central chemoreceptors monitor a fluctuation within the pH and have the biggest effect. Approximately 3/4 of the change in respiratory rhythm is going to be induced by the pH shift that they detect. As carbon dioxide goes across the blood-brain barrier, it's going to get into the cerebral spinal fluid and form carbonic acid within the cerebral spinal fluid by reacting with water in the CSF. That carbonic acid will then release hydrogen ions into the solution, and those dissolved hydrogen ions will then stimulate the chemoreceptors, and it has a huge effect on those chemoreceptors because the cerebral spinal fluid doesn't have a lot of proteins within it to buffer the large fluctuation in pH that those hydrogen ions cause. So hydrogen ions, in particular hydrogen ions have the greatest effect. In particular, hydrogen ions within the cerebral spinal fluid have a much stronger effect than hydrogen ions within the blood. Although within the blood, we still are going to have a notable effect. About 25% of the respiratory rhythm response is going to be due to blood pH fluctuations. And if you're looking at this, our hydrogen ions, the 75 and 25 refers to the change in respiratory rhythm due to a blood pH fluctuation from the hydrogen ions. There are still other factors at play, the carbon dioxide and the oxygen gases. So if we have a blood pH below 7.35, that is known as blood acidosis. Our blood is too acidic. If we have a blood pH above 7.45, we have alkalosis. Our blood is too basic or too alkaline. We also can look at carbon dioxide levels. If we have too little carbon dioxide, we have hypoxia, and that's formally defined as less than 37 millimeters of mercury for a partial pressure. Low blood carbon dioxide is the single greatest cause of blood alkalosis, because if we don't have enough carbon dioxide, we can't make enough carbonic acid, and then our blood becomes too alkaline. If we have hypercapnia, we have too much blood carbon dioxide, a concentration greater than 43 millimeters of mercury for its partial pressure. And if we have too much carbon dioxide, we're going to have too much carbonic acid, which results in acidosis. So too much carbon dioxide is the single greatest cause of our blood becoming too acidic, of the blood pH dropping below 7.35. So let's say you hold your breath for a really long time. Holding your breath is going to induce hypercapnia because carbon dioxide builds up in your blood. As the carbon dioxide builds up, you're going to have more acid, And the hypercapnia directly leads to acidosis of your bloodstream when you hold your breath too long. So as we look at respiratory acidosis and respiratory alkalosis, so either our blood pH being too acidic or too alkaline because of an inappropriate respiratory rhythm, the blood pH ultimately is going to be mismatched between our pulmonary ventilation and our CO2 production. So we're breathing in and out too much relative to the amount of carbon dioxide we're producing, or we're breathing in and out too little relative to the amount of carbon dioxide we're producing. Our rate of breathing in and out doesn't match or correspond to the amount of carbon dioxide within our blood. So let's say we have respiratory acidosis in place. So we have too much acid in our bloodstream. What can we do? We can hyperventilate. And if we hyperventilate, we blow off excess CO2. By getting rid of the excess CO2, we're going to cause the hydrogen ion concentration in the blood to go down as we expire more carbon dioxide. And then this will reduce the amount of acid in the blood, ultimately raising blood pH back to homeostasis. If we are not breathing enough, we have hypoventilation. That could be something we use to correct alkalosis. So if our blood is too alkaline, we need to add more carbon dioxide into the blood so that we can make more acid to make the blood more acidic to correct the alkaline nature of the blood. So we will build up and accumulate carbon dioxide, and as we have more and more carbon dioxide, we produce more carbonic acid, and more carbonic acid results in more hydrogen ions in the bloodstream, ultimately lowering blood pH and restoring homeostasis. We also can have a condition known as ketoacidosis. Ketoacidosis is sometimes referred to as metabolic acidosis as opposed to respiratory acidosis. So during ketoacidosis, we have acidic blood, but this acidic blood is because we're burning through fat very quickly. As we burn through fat quickly, we are going to produce ketone bodies. These ketone bodies are then going to be acidic in nature. So here is the reaction mechanisms. Normally, we'll take fatty acids and convert those fatty acids to acetyl-CoA, and then acetyl-CoA is converted to acetoacetyl-CoA, and then that is converted to acetoacetate, and that can spontaneously be converted to a ketone, acetone, and a carbon dioxide. And as we have more carbon dioxide, we become more acidic. We can also have a buildup of ketone bodies during this process. So ketoacidosis is when we have excessive ketone bodies correlating with an acidic blood. This is a classic symptom of diabetes mellitus, or when type 1 diabetes is initially setting in. A lot of times that individual will lose fat from their body very rapidly, and they'll have ketoacidosis as a result. And this can cause the individual to have a Kussmaul respiration. And this should be a subscripted 2 right there. It should be CO2. I forgot to subscript this CO2. This Kussmaul respiration is when we're hyperventilating to compensate for, or partially compensate for the fact that our metabolism is dumping too many acidic ketone bodies into our bloodstream. And diabetes mellitus, in addition to corresponding to ketoacidosis, is also going to correspond to an increase in those ketone bodies within the urine and really sweet tasting urine. You'll have an increase in glucose concentrations within the urine as well, which is why I included the P cup diagram. As we look at indirect effects of carbon dioxide on breathing, we can have through pH. Carbon dioxide can influence our respiratory rhythm indirectly. We've already talked about that pretty thoroughly in a lot of detail. Directly, though, as we have an increase of carbon dioxide when we start exercising, that's going to stimulate our chemoreceptors to cause us to breathe in and out more. But notably, it's our peripheral chemoreceptors, not our central chemoreceptors. It takes time for carbon dioxide to go from the bloodstream to the cerebrospinal fluid to the central chemoreceptors. So the peripheral chemoreceptors within the blood vessels outside of the central nervous system are going to be able to respond more rapidly. As we look at blood oxygen levels, it has very little effect on respiration. We can have chronic hypoxia. This is chronic low oxygen. If our oxygen levels are less than 60 millimeters of mercury for a significant amount of time, that can cause us to have ventilation increased. This is known as hypoxic drive. As we have low blood oxygen levels, eventually that will cause us to breathe in and out more. That'll increase the respiratory rhythm. Hypoxic drive can be stimulated, or chronic hypoxia can be stimulated or triggered by emphysema or pneumonia or remaining at a high altitude for several days continuously. Let's talk about application here. Here's a good tangential story for you. When my wife was on the swim team, her swim coach made it very clear to everyone that you were not supposed to hyperventilate before you jumped into the pool to swim laps. A lot of high school students like to hyperventilate before they go swimming because they can hold their breath for longer after hyperventilating, so they don't have to stick their head out of the water to breathe. The thing about hyperventilating is that when you hyperventilate, you don't cause there to be more oxygen in your bloodstream. Instead, you artificially lower blood carbon dioxide and blood pH levels. So it's not that you're pumping more oxygen into your blood, you're just getting rid of excess carbon dioxide by hyperventilating before swimming laps in the pool. And that's a bad thing because you can cause your blood oxygen levels to crash relative to your blood carbon dioxide levels if you hyperventilate before swimming laps or immediately before swimming laps in a swimming pool. So generally speaking, don't do that. Just breathe normally. It's the best. This will be our last slide for the presentation. As we look at respiration and exercise, we find that our respiratory rhythm, respiration goes up during exercises whenever our brain says motor commands to muscles. Just thinking about exercising causes you to breathe more. So there's something, I mean, if you want to sit on the couch and just watch an exercise video, that's going to cause your respiratory rhythm to go up. There's something about anticipating the exercise that causes your body to subconsciously increase the respiratory rhythm to accommodate for the change to the muscle's metabolic needs. Also, if we stimulate proprioceptors, so this is some cool science that was done, and the laboratory experiments that were done involved just taking a patient and moving their joints and just moving their body for them. So they weren't doing it, but moving it for them activated the proprioceptors on their body and caused them to breathe in and out more, had an elevation of respiratory rhythm. So increased breathing happens when muscles move, even if you're not voluntarily moving those muscles. And that increase in pulmonary ventilation is going to help us to keep our blood gas values at their homeostatic levels in anticipation of elevated O2 consumption and elevated CO2 generation by those muscles. That's all we have for this recording. If you have any questions or comments, please feel free to post them in the class discussion board or to shoot me an email. And as always, happy studies.